Okay, I'm going to be adding fuel to the fire of that last discussion by continuing. But yes, hi, thank you for having me. My name is Matt. I'm a physicist, technologist, and educator. Each of those three things is going to be important for what I'm going to be talking about, which is advanced quantum simulations with QuTiP, a gateway to understanding anomalies in hydrogen-loaded metals. A lot to talk about. We'll unpack it. I'll also do a live demo of this, so hopefully you're looking forward to a bit of live coding. Before I get into things, a few words, firstly about who this is done with. So it's not just me. There is Florian Metzler, who's at the back there, Jonah Messenger, who you just saw, and we've also got Nicola Galvanetto, and of course, Peter Hagelstein, whose work kind of inspired all of this, which wouldn't have been possible without the generous support of the Anthropocene Institute. So thank you very much for that. Okay, a few words, a little bit about me, because I'm kind of new to the learner stage, so you might be thinking, who is this Matt guy? Why should I trust anything that comes out of his mouth? So my background is originally in hot fusion research, so conventional fusion, tokamak stuff. 10 years of my professional life at the beginning was doing that work at Imperial College, the Cullum Center for Fusion Energy, where I did experiments, but mainly focused on theory and simulation, bits of which you can see on the screen here. Back in those days, before 2014, I was very much kind of anti-cold fusion. I was like the nemesis. I remember when Rossi came out with his stuff in 2011, I just thought crackpot science and moved on. Little did I know that there is a lot of interesting things that were worth paying attention to in this field. It took me a while, but I started paying attention around 2017. And by 2020, I'd fully transitioned to the dark side, you might say. I did my own experiments. That's where I started 5 years ago now. Didn't work out. Most of them don't. And then I got connected with Florian and Peter in around 2019, 2020. And then we started to talk more about theory, more about simulation. And this has kind of culminated with this kind of tutorial series on excitation transfer, which is what Jonah was talking about. And I'll show you some of those tutorials later. And of course, this 200-page document that Jonah was describing on the known mechanisms that can increase nuclear fusion rates in solid state. And there is some controversy, as we can tell from the audience, but that's kind of good. Scientific controversy is what pushes us forward. So between full-time academic and today, I also had a stint in technology, did some coding application stuff, and also taught people about technology. And one of the things that comes up in those sessions, which I still do, is the transformative effect of open source technologies that to transform any field. And I think Lena is no exception to that, and we'll see today a specific open source tool which can, in principle, help to shift Lena from fringe science into a kind of a more engineering kind of discipline. That's the hope, that's the aspiration that I'm going to kind of try and articulate in the rest of my talk. So, what am I going to be talking about? You can think of this as kind of a follow-on talk from what Jonah was describing, in a sense, taking seriously the ideas that Peter Hagelstein is putting forward and kind of saying, well, what next from that? And the summary of his talk, paraphrasing grossly, is that Lena is just quantum physics. That's essentially what Jonah was saying. That's essentially what Peter is saying. Of course, it's more detailed than that. Excitation transfer, the specific mechanism is what Peter's really focusing on. But zoomed out, this is really just conventional quantum physics. Now, this is great, and I'll explain why it's great in a second. But before I do, I want to just emphasize this word just here. Anyone who has listened to a talk by Peter or engaged with his work will know that it's not just, is it? It's not really just. These are really his equations, I joke you not. It's not Peter's fault. Quantum physics is hard, right, for anybody. So yes, it's just conventional quantum physics, but it doesn't make it easy. The point I'm making, though, is that because it's just quantum physics, we can use existing techniques, tools, and software. It's very empowering. We don't have to go and discover some exotic new particle, wait for it to be characterized before we can make progress. No, we have tools and techniques that can help us. So it's a kind of a very empowering message, and it's the kind of thing that can hopefully shift our attention from we just take what nature gives us to us systematically designing experiments, materials that can work for us, and then we can hopefully be able to simulate those materials and experiments confidently. That's kind of the idea, and that's basically engineering. So I guess the provocation I'm putting forward is that in LENR we might actually be able to start doing some engineering if the hypothesis, the working hypothesis that Peter put forward is correct. You might think that's a bit outlandish, but it's done in other complicated fields. So yes, LENR is complicated, but it is not uniquely so. In biology, they do this kind of thing all the time. They don't call it engineering, they call it a rational design. So with advances in computation and simulation, they design molecules that behave in specific ways that can target, for example, specific kinds of cancer. They design them, they build them, they test them, and so on. And if they can do this in biology, it's a very messy field. Why can't we do the same? That's the aspiration. Of course, the devil is in the detail, it always is. So what I want to do really for the rest of the talk is to expose you to a little bit of that detail, a little bit because we're really just at the beginning of the journey of trying to create this kind of rational design for LENR, but I wanted to expose you to a bit of that. So what I'm going to do now is look at a specific open source tool that we've been using to do quantum simulations, and then I'm going to do a little live demo. So this tool is called QuTiP, which stands for Quantum Toolbox in Python. And it's open source, which means it's free to use, free to improve upon, and it's got a really excellent community and documentation. What this means is that I don't have to spend 5 years getting a PhD in specific quantum simulation techniques in order to start using this. I can use it pretty much immediately. And I'm skilled, I got my PhD in plasma physics, so it's not quantum, and nevertheless I can use these tools because of that open source nature. In addition, because it's open source, it means we can have the hope of composing it with other tools to, in principle, create a kind of a computational workbench from which we can start designing LENR systems from the ground up. That's the idea. Word of caution, though, I'm giving this vibe that these tools are accessible and we can use them and anyone can use them. This is not what I'm talking about. We're not going to have the situation where your grandmother's going to start coding up quantum simulations. That's not what I'm talking about. I'm talking about people who have some skill, some experience, can use these tools without having to be, have a PhD immediately to get started. All right, that's the preamble. Now what we're going to do is I'm going to demonstrate some of this excitation transfer that Jonah was describing in his talk, but live in front of you using QuTiP. The reason that I'm going to do this is twofold. Firstly, I want you to see that you don't have to take Jonah's word for it. You don't have to take Peter's word for it. You can start to simulate these things and see the results in front of your eyes. That's the first thing. Second thing, and the reason why I want to do this, is I want you to start imagining, as I'm going to take you through a kind of almost tutorial-like vibe, I want you to think, imagine we added more realism to these simulations. What could we do next? That's kind of the second reason I want to do this. We're going to look at one little piece of excitation transfer, and I want to kind of deal with one specific objection. Unfortunately, it's not the objections that came up in the questions just now, but the objection is going to be connected to this kind of idea, which is an idealized view that is not going to be the physical view in the end. We've got the idea that the deuterium molecule is an excited state of helium-4. That's the kind of concept that Julian Schwinger kind of gave us. The 24 MeV of fusion energy, which comes from the fusion of deuterium, so dropping down into the helium-4 state, that's got to move somewhere. And in this excitation transfer view of things, it moves across, somehow, to the palladium. And in this vision, I'm imagining a single palladium is absorbing all of that 24 MeV. In reality, it might be several palladium, but just for the sake of this demonstration, a single palladium is going to absorb it. Now, the objection that I'm going to, in a sense, debunk through simulation in front of your eyes is the one that people often have, particularly when they're coming from hot fusion. They say, look, there's 24 MeV of fusion energy, millions of electron volts. How the hell are you going to move that from one place to another when it's mediated through these itty-bitty vibrations? Phonons that have nano electron volt level. There's 15 orders of magnitude difference. Just not possible. Well, I will show you that it's possible with QuTiP. For that, we need to move from a pictorial view to a mathematical view. So this is the Hamiltonian. So this is God for all intents and purposes in the quantum world. The Hamiltonian describes everything. The energy of the different parts of the system and the way that they interact together. For those of you who are not interested in the detail, just know all of these symbols are standard, textbook. There's nothing controversial that's written on screen. For those of you who are interested in the detail, here is the nuclear stuff. So this is deuterium, palladium. We have the same nuclear energy, that's this delta E. That will be the 24 MeV if we were putting all physical numbers in. This is the vibrations of the lattice, the phonons, but could be photons, depending on what number you put in for this h bar omega. And these last two terms imbue the system with the ability to create vibrations, to destroy vibrations, to shift the levels in the nuclear system. So those are the three pieces. That now needs to get turned into computer code, but this is where QuTiP comes in. And now we're going to go over to the world of Jupyter Lab. So we're going to do a bit of coding together. So I'm going to create a computational notebook, which is a place where you write documentation, code, and you see results of your simulation all in one place. It's a de facto standard these days, and so I'm going to show you an example that I made earlier, a short one. I'm not going to code it live completely because I'll just make lots of mistakes. What I want you to think as I'm going through this, I'm kind of teaching you some stuff, but again, I want you to keep in your mind, imagine if I start adding more levels of realism, where could we get to in the months and years ahead? Think of that computational workbench that we could eventually get to. All right, now let's just check. I need to zoom in on this. At the back, Florian, do I need to zoom in a bit more? Yeah, good. One more. Okay, so we start with a bit of documentation. Risky live quantum demo. They're always risky because computers are fickle. And then it says, first, let's bring in the tools we need. QuTiP, import it, boom. I now have all the powers to simulate quantum things. And a bit of a helper function here coming in. This is the kind of code that Granny can't make. This is the bit that I've made to help make QuTiP a little bit easier to use for our particular purposes. Then I've written this Hamiltonian, the thing that describes the whole system. Remember I said it's standard. What this means is all of the symbols you see on the screen can be created in QuTiP. It's a standard, so I don't have to reinvent the wheel. So let's go ahead and make those things. And now I have the ability to go and tweak these numbers. So what is the nuclear energy? What is the phonon energy? What is the coupling, the interaction between those two? Now we can start tweaking with these numbers, and it's by changing those numbers that we start to simulate different kinds of systems. All right, let's make a Hamiltonian, shall we? Let's start with D2, and let's start with some vibrations, okay? The nuclear energy has 1, right? So do the vibrations right now. This is not the system that we're going to want to end up with, but we're just getting started. Hamiltonian, boom, done. Now we simulate, bum, done, visualize. Here we go. Now I need to zoom out again. What are you looking at? Probability against time. I'm sorry, it's gone a bit small now, but I have to fit it all in on the screen. Probability on the vertical, time on the horizontal. Quantum mechanics, everything's probabilistic. It's saying that we start off in the orange state, and we stay there for all time. It's a very boring simulation. What is this orange state? It's described by 3 numbers here. First number describes the vibrations, the phonons. 0, there's no vibrations. I started with nothing. Second number is the deuterium. If it's 1, it means that D2 is still there. If it's 0, it means fusion has happened. So we've still got D2 right now because it's a number 1. The third number is the palladium. 0 means it's in the ground state. So all the excitation is in the deuterium. It's waiting to fuse, and it's waiting there for all time, apparently. Nothing is happening. Anyone know why nothing's happening? Quiz?
Coupling.
Thank you. No, we haven't put the coupling in. Right, we can do that. Add some coupling. Let's do interaction D2. Now the deuterium can talk to the vibrations. Easy peasy. 1, 2, 3, 4, 5. Lovely. Now there's some dynamics. We move between the orange and the gray. Well, I've just told you what the orange is. That's the deuterium waiting to fuse. Look at the gray one. What's happened to the excitation in the deuterium, which is that second number? Where has it gone? It's gone to 0, and it's moved into the lattice. It's moved into the vibrations. That's what that 1 is in the first column. So apparently all of that fusion energy, 24 MeV, has been taken up by the lattice, which is outrageous because that's not how it works. You can't have a single quantum of vibration, a single phonon carrying 24 MeV. This is more like what you would get with a photon, like a gamma ray carrying all the energy. In order to simulate the systems that we're interested in, where the phonons have tiny, tiny energy, I would have to make this number, this D2 number, extremely large, 15 orders of magnitude bigger. And then I would be simulating something that's more realistic. It would take a very long time to do that, so I'm just going to make it 10.5 for now, just for demonstration purposes. But what you're going to see now is that nothing's going to happen, because the phonons have an energy of 1. The nuclear energy is 10.5. Now, 0.5 is important. You can't shift a fraction of a quantum. That's not how quantum physics works. So when I do this, nothing happens. The system stays in an unfused state. And in principle, the same thing would happen if I added the palladium in. So let's add the palladium, right? Same energy as the deuterium, right? So they're kind of resonant. I've got the donor thing, which is the deuterium. The receiver is the palladium. But because the vibrations are on a completely different energy scale, how can they possibly accommodate this 10.5? Or, the realistic number would be millions of electron volts. It shouldn't happen. And let's add the interaction between the lattice and the palladium. Simulate, 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 simulate. Nothing happens. Or does it? Let's simulate for a bit longer. Something is starting to change. One more. Look at that. Now, let's just take a moment. We move from the orange state, where the deuterium is there. It hasn't fused yet. We're moving now to the green state. Where's the energy gone? From the deuterium into where? Into the palladium, right? Orange to green. Now, how much phonon energy do I have? Can anyone spot that? Orange to green. It's 0. I deliberately started off with no phonons at all, no vibrations, and yet I can move all this energy from one place to another. And by the way, I could have put 1 billion in here and it still would have happened. So this is the really surprising thing that you don't need to take my word for. It's just simulating, it's solving the Schrodinger equation in front of your eyes. You can move MeV of energy from one place to another, even if there's no vibrations happening at all. Just the existence of this vibrational field is enough to make that coupling. It's a very surprising effect of quantum mechanics, but it's not anything that's not standard. So I wanted to just kind of demonstrate that to you. There's many more weird things about excitation transfer that you might want to know about and dig into. You can do with QuTiP. We don't have time to do it today. And I'll just say, how much time do I have?
We have about 1 more minute.
All right. So I will just say that...
No, 1 more minute before I give you that. So
Okay, amazing. 3 minutes, we can do this. So I'll just say that we've been kind of digging a bit deeper into these things for tutorial-like purposes. We've put these notebooks on GitHub, and you can go and investigate them if you want. So we've explored things like, well, why is excitation transfer so slow? And how can you speed it up? Jonah was talking about Dicke enhancement. We explore that and other things too, which we don't have time to talk about. Breaking destructive interference. If anyone's interested in that, you can come and talk to me afterwards. It's really super interesting. But these are all ready for you to go and play with. If you don't have the software on your computer, no worries. You can go and run them in the cloud. So the final thing I want to kind of come to in kind of closing really is, what does this mean for the rational design for LENR? Where do we go from here? I've kind of exposed you to like one piece that we think is one piece of the puzzle that can create a kind of software suite that can simulate all kinds of things for LENR. Ideally, we want to get to the point of experimental inputs to outputs. So you have lattice structure, lattice composition, lattice stimulation. These are the things we can control. And then they're going to affect all these things in the middle. And we need simulation tools for each of those things. Some of them we have some experience with, like QuTiP. Others we don't. So we're kind of, in a sense, looking to the community here and other communities to help us pull together those different bits of software. As you saw, QuTiP is one of those to help us simulate things like excitation transfer. We know there's things like Quantum Espresso, another open source technology that helps to simulate the different vibrational modes. And actually, in Jonah's last talk, you saw there was a lattice that was actually vibrating around. That was a simulation that Florian did involving Quantum Espresso. So that was kind of real density functional theory. But we need to look at things like molecular dynamics codes, nuclear shell models. I've never run nuclear codes, but in principle, these can be run. And then in principle, all of the outputs from each can be combined together to create this software suite from which we can have a rational design for LENR and take that more engineering approach. This is all assuming that the ideas that Peter has talked about are correct. There is, of course, questions that we've had already here today, and I look forward to kind of getting involved in some of those discussions afterwards. So thank you very much for your time and attention.
Thank you, Matt Lilley. And we're ready to take some questions. Yes, Dan, and then we'll do Dimitar.
Wow, I did that in 20 minutes. That was faster than I expected.
The issue here is much the same as in Matt's talk. How are you dealing with entropy change? In other words, losses in these systems. All of them have to succumb to the second law of thermodynamics, and yet I'm not hearing you talk about what is the third term in your Hamiltonian.
Yeah, so in principle, losses can be included in QuTiP. So in this particular simulation, there are no losses, but you can include those.
And what about the conservation laws? This is one of the problems in quantum physics. That in many cases, in most cases, there's no check on the energy and mass conservation in the model.
So
and
energy.
That's what has always troubled me about Peter's models.
Yeah.
There's no energy and mass conservation check.
So I'll just say I'm definitely not in. I'm not saying that I know all the solutions for quantum mechanics. So people have problems with energy conservation. I know that, things like virtual states that violate energy conservation. I don't claim to be able to fix those problems. But in general, what I found is that energy conservation in quantum mechanics always happens in the end. So when you're evolving the systems, energy can be not conserved, but in the end, it always has to be conserved. So that is true. Yeah. So in terms of entropy stuff, I mean, the Schrödinger equation doesn't say anything about entropy. It's kind of a separate thing. But I'd love to chat to you more about that. But you can definitely include loss in the models if you want to. That's for sure.
Okay, maybe I have missed something, but in your Hamiltonian, I didn't see the term describing electron-phonon coupling.
This one.
Electron-phonon coupling.
Oh, so electron-phonon coupling?
Yes.
Yeah.
You have
sure.
actually crystal lattice, okay?
Yeah.
And you must account significantly, especially the coupling between phonons and the valence electrons.
So you're saying electrons and phonons?
Valence, yes.
Sure. What do you expect they will do to the nuclear story? Because there's lots of things that you could include in any physical model.
Yes, I'm going to tell you.
Yeah.
Generally speaking, it is connected with localization of the electrons in the crystal lattice, doing electrical screening. That's why I'm not sure that actually using density functional theory is a good idea, because actually it provides opportunity you to calculate a periodical structure. But in case of local interactions, density functional theory doesn't work. Thanks.
Okay. I'd like to talk to you more about that.
Okay, yes, sir.
It's more about a comment. All of these seem more like a software development presentation. I mean, this package is more like hiding the physics than revealing it. How is it going to help to develop more experiments or even to build Leonard systems?
Yeah.
Also because probably not all the physics is known. So codifying it into a software and then hiding it between interface layers might be premature, and even it might damage the pace of research.
Nah, so it's not. Well, damage, absolutely not. Definitely not.
Okay,
but I can still talk to you.
The point is that even the Hamiltonian, even if you add all the terms possible, it's still a high-level description of the system. It's already an abstraction level in itself. We are dealing with atoms and molecules and lattices.
Sorry, so let's mean to say the Hamiltonian. So I take your point on the software thing. Yeah. The Hamiltonian describes absolutely everything. There's nothing missing from. If you write a complete Hamiltonian, it describes absolutely everything. So I think you're not quite correct on that.
You are the one making the choice on how many terms you include.
Correct.
So there must be a human choice at the beginning.
There is, and this is the problem of simulating any physical system. So in the world that I came from originally in plasma physics, we have so many particles.
You also come from plasma physics.
Yeah, well, so you have to make some approximations. And,
yeah,
and
but
I mean,
they are chosen by the experimentalist or the researcher.
Yeah, and I think so. Well, so absolutely. And this last slide I put on here which is like composing these different models together. This is precisely answering your question of like, you have to have different models for different things. So if you want to understand how the lattice vibrates, you need to run some molecular dynamics codes. That gives you an input into the next code and so on. And the idea is that you try and start from what are the things that the engineers know, which is like the structure of the lattice, composition, stimulation, and those should then feed into codes that then give you outputs that tell you exactly how the system behaves. I mean, this is kind of what you're always after, but if your question is that you're not confident that we have all the right codes, I 100% agree. We're just getting started in this. And so if there's anything missing from this slide, which for sure there will be, I'm totally open to input on that.
Okay, thank you.
But we have to. But in a sense, we have to start somewhere. Right?
I'm just perplexed. There's nothing.
No, it's okay. But you always have to start somewhere. So we think that if the biologists can do this, then we should start doing this. And look, this might all be wrong. Peter's theory might all end up being wrong, and that's the kind of risk that we take. But we think that there's enough confidence to be able to push forward, and so that's kind of the vibe that we're going for.
Okay, my point is, the Hamiltonian you have presented is very simple. And of course, if you use this Hamiltonian, you can present something like this. Now it's better, okay. The point is, our Hamiltonian is very simple. Something too simple, of course.
Of course.
There are many things which are missing there. Mm-hmm. And your example with, with two energy levels exciting and de-exciting, there is a simple quantum mechanical example, from the first years of the study, that you have a, isolated state, mm-hmm. and you have two levels that are changing, This is a very simple case. So this is something what we know. The problem is something else. So there is wavelengths. If you have 10 million phonons, you want to construct 24 MeV energy. Yeah, this I think there's you need even 200 million phonons. Mm-hmm. What is the wavelength of the phonons mm-hmm. to construct really a coherent state? And we know what is the wavelength. It's not so large. Mm-hmm. And you have no so large density of phonons in the solid state. So there is the first point. The second point, it is... So
if I just clarify, so that means that you just don't think that you can have enough phonons in the lattice at all? Is that what you're saying?
Of course. We know what is the density of phonons mm-hmm. in the lattice mm-hmm. very well. Mm-hmm. And the second one is we know also what kind of coherence we can expect in the solids. We measure, for instance, neutron scattering at cold neutrons you can use at energies, 20 milli-electron volts or something like this. So we know the physics very well. All the physics is quantum physics. There is nothing very special, okay?
If I might say, there are some people who would speculate that actually there are exotic mechanisms at play. So I think
we know this physics very well. Mm. So we don't need to discover something completely new particles, new physics. No, there is the same physics. And this third point, if you want to transfer energy from helium or two neutrons to palladium, you should calculate the transition probability, not according to your Hamiltonian, because what is important, the position helium or neutrons compared to the palladium atom. And then you have, of course, to include also Coulomb barrier between them. It's not so easy. If you have even molecules, which seems to be coherent, if you want to calculate the fusion of two atoms within molecules, you should take into account the Coulomb barrier between.
Sure. So that. Yeah. So do you think? Is it my understanding that you think that I don't think the Coulomb barrier exists?
I think this physics is not correct.
So the Coulomb barrier would just be a different U here. That's all that is.
Yeah, there's, but it's a large factor. There is,
Yeah.
There's many orders of magnitude. Okay.
That absolutely makes sense. So this Hamiltonian is just for demonstration purposes, and everything that Jonah was describing, which is including all the Coulomb barrier effects, is absolutely there and real, and I definitely don't deny the Coulomb barrier exists for sure.
Just a quick comment that I think applies to, I'm Florian, I've been working on this with Matt and Peter and Jonah. That a quick comment that applies to both Konrad's remarks and also Tiziano's remarks. This is all about what is the level of abstraction you want to operate on, right? And then the basic principle here is Occam's razor, right? You want to start at a high level of abstraction, and then you want to get deeper and deeper and add more and more detail as much as necessary. There's this quote attributed to Einstein, as simple as possible, but as complicated as necessary, right? And so you go and add more and more detail until you get you're able to describe, to relate the inputs to the outputs. And the inputs in our case are the experimental parameters like the dissipated photon power and the lattice geometry and the lattice composition and the nuclear states of that. These are the experimental inputs, and the outputs are the reaction rates as reported by many of the people in this room, and the reaction products, where there's neutrons, alphas, and so on. And in the paper that will come out in a couple of weeks, you will see we will have more complicated Hamiltonians, and Matt emphasized that this was just a simple demonstration. We'll have more complicated Hamiltonians, but they're not comprehensive in the sense that they describe everything, otherwise they would be computationally untractable, but they're sufficiently detailed to describe, to relate all the experimental parameters to all the experimental outcomes that people have reported. And for us, that's the sweet spot in terms of what you want from a model. And so that's the level of abstraction that the actual work is on.
Okay. I think, are there any further questions? If not, then thank you, Matt, Lilley.
Thank you.
Thank you very much.